แล้วบางทีช่องจะชนมันไม่ดูรูปกับดูคนเฮ้ยมันไม่กล้าพูดอะไรเขาชนอย่างนี้นึกว่าซีซั่นนี้จะไม่ได้เปิดเลย
If we finish these lectures with any time to spare, I'll show you a game or I'll show you a video. But I don't think we'll have any time spare because we've got 2 topics left. Question.
Why bus topology is full duplex and 82.3 is half duplex?
I think if you go back to the slides, there were different. Originally, Ethernet using the bus topology. Only one node could transmit at a time, because if 2 transmitted, there'd be a collision. So you could either transmit or receive. So it was a half duplex setup in the original case.
In CSMCD, we have listened to other people. If other people send, we have not sending. So this is a half duplex. We waiting for the empty time that I can send.
Yes, you listen. If no one else is transmitting, then you can transmit. So you need to listen to what others are transmitting.
This is a half duplex.
This is CSMA. This is the MAC control.
Not.
But it only makes when you don't need to share amongst users, then using full duplex becomes very useful, because in a normal Ethernet that we have here, where we have a star-based topology, everyone has a dedicated link, and in fact we basically have 2 links, one uplink to the switch and one downlink. So we two pairs of wires. So that's full duplex. So essentially having 2 links, because you can then transmit and receive at one time.
Only one, this is half duplex, but we have 2 links, so we have up and down with full duplex.
Yes, if in a bus topology we tried that, we could have 2 separate links, but I don't think it will improve much, because you still have to listen and wait for someone else to transmit.
So bus is a half of
half duplex, yeah, in the original form.
Nothing in S02.3 is a full duplex. Everything is half duplex.
But the switched Ethernet is 802.3, and that is full duplex. So yes, in the past there was half duplex links, and now there are full duplex links.
Because we have 2 lines.
Yeah. I can make full duplex by buying 2 different cables and joining them together.
So everything
Essentially.
like half duplex, and if you want to full duplex, you add up and 1 line.
That's, in terms of LANs, that's a typical way to do it, to have a separate cable to provide full duplex. Yeah. You have 2 different transmission mediums, the transmitter.
If 2 people send together in the same time, we cannot know that each form is signal form. We have to wait.
Yes, if you've just got a single medium, then having 2 people transmit at the same time is a problem we want to avoid.
Thank you.
Internet addresses. We know that, so we're going to go quite quickly through IP addresses, but try and follow, because you'll need to do some examples before the next quiz. So we know that IP addresses are 32 bits. Of those 32 bits, some bits are used to identify the network or the subnet of the device. That is, this is one network. This is a device attached to that network. This device is going to have a 32-bit address. Some of those bits will identify the network it's attached to, and the rest of those bits will identify the device within that network. So we talk about the IP address having 2 portions, 2 parts, the network portion and the host portion. We're going to explain how do we determine which part is the network and which part is the host portion shortly, the split between the 2. You know how to convert a 32-bit IP address into a dotted decimal notation, and you need to be able to do those calculations quite quickly. split it into 4 8-bit parts, convert each 8-bit number into a decimal value, and join those 4 decimal values separated by dots. So that can be applied to any 32-bit IP address. So we're going to talk about how do we split between the network portion and host portion. We're going to use this example to illustrate it. The concept is that, so in this case we have 3 networks, 2 routers, 4 hosts. Each of those hosts are going to have an IP address. In fact, the routers will as well, but we'll focus on the hosts. And the structure of that IP address, those 32 bits, is that something will identify the subnet, or the network, network A, host 2 is attached to network A, and some bits will identify the device, let's say 2. This is not an IP address, but the concept is part of the address identifies the network, part of the address identifies the host. This would be A1, this would be C4, and C3. So the rules are, with IP addresses, all networks in our internet must have a different network portion of the address. This is A, B, and C. It cannot be A, B, and B. They must be unique within the internet. All devices that attach to a one network must have a unique host portion of the address. 2 and 1. They cannot be the same. You need to have unique addresses so you can know who is communicating. All devices attached to a one subnet, one network, must have the same network portion of the address. A1, A2, and in fact the router may have an address as well, A3. They're all attached to the same network, they all need the same network portion. Our IP address is not a letter and a number, it's 32 bits, so we'll look at how do we structure the split between the network and the host portion, using some examples. Let's focus on, and I'll do it over here, host A1. I'll give it an IP address and then we'll use that as an example to explain some of these concepts. So I'll give it a 32-bit IP address. Bits, I've just separated by spaces just so we can identify quickly the dotted decimal form. To convert to the dotted decimal notation, we find the decimal value of this, which is 16. I'll write the address over here, 16, 192, 0, 1. 16.192.0.1 is just the dotted decimal notation of this real IP address. Some parts of this 32-bit address identify the subnet or the network, network A, and some parts identify the host or the device, device 1. The split is usually given as which bits identify the network and which identify the host. In this example, let's say the split is after 10 bits, which means that the first 10 bits in our IP address identify the network. Isn't what 8? Maybe I've got a 0 in the wrong spot somewhere. There should be a 0 here. I want it to be 16. My example is 16, but I've missed a 0. 16, 192, 0, 1. Thank you. Let's say in this example, we're going to split the address into two parts. And the split is after the 10th bit. 10 bits followed by 22 bits. This, in the example, we'll say is the network portion of the address, and the rest is the host portion. So some bits identify the network, and some bits identify the host. We'll talk later about how do we know that the split is after 10 bits. Just in this example, we've said it's at 10 bits. If this is true, then let's consider host A2, our other host on the same subnet. Then host A2 must have the same first 10 bits. That's the rule that we must follow. It's on the same network. The network portion of the address must be the same between those two hosts. So the first 10 bits must be the same between those two hosts. The remaining 22 bits must be different. The two hosts are on the same network. They must have unique host portions. Different. This value is different from this. You see that there's only these two bits differ. In fact, we can quickly calculate that this would be 16.192.0.2. So these two addresses meet our requirements of the same network portion but different host portion for the hosts on the same network. To determine where the split is between the network and the host portion, we use what's called a subnet mask. In the past, there are different ways to determine how to split an IP address into the two parts. Originally, there was what's called classful addressing, and there were some improvements, and what leads to today of classless addressing, which is the only concept we're going to focus on in this lecture. And how it works is that, in fact, your device has two addresses. It has an IP address, such as this, and it has some other identifier that tells us where is the split between the network and host portion. And that other identifier is called a subnet mask, or an address mask, or simply a mask. It is a 32-bit value where if we have a bit 1, it indicates the corresponding bit of the IP address is in the network portion, and if we have a bit 0, it means the corresponding bit is in the host portion. So the mask is used to tell us where do we split between network and host. In this example, after 10 bits. In a different example, maybe after 11 bits, 23 bits. It depends upon the mask. So the mask in this example the first 10 bits identify the network, therefore in the mask the first 10 bits must be 1. The last 22 bits identify the host, the last 22 bits must be 0. So in fact, a device has two identifiers, the IP address and the subnet mask. You can think they go together. We need to know both to know the full information about the address of that device. I chose a mask in this case. I chose this mask, which in fact means that the first 10 bits are the network portion. It doesn't have to be this mask. It can be different. We'll see an example of a different one. And the mask is applied to all the hosts or all the devices in that network. The the mask is a 32-bit value. We can also write it in dotted decimal notation. Just convert it to 8 ones in decimal is 255, 255. 1 1 followed by 6 zeros is 192, 0 0. So the identifier of host A1 in our example on the other side is that it has an IP address 16.192.0.1 and a subnet mask of 255.192.0.0. This subnet mask tells the device that in fact the first 10 bits of its address represent the network it's on, the last 22 represent the host within that network. And similar, host A2 has this IP address and this subnet mask. So in fact our addresses are always in 32-bit values, but just the human readable forms we can convert to the dotted decimal notation. With a subnet mask there's even a shorter form. Because it's the first 10 bits, another form to write the subnet mask is simply /10. This slash notation means the first 10 bits identify the network portion. So this value is the same as this, which is the same as this. 3 values of the same subnet mask. So host A1 has an IP address 16.192.0.1/10 in our example. And host A2 is 16.192.0.1, also 0.2, sorry, /10. So that's a common way that you'll see IP addresses written. Include their subnet mask. Or you may see the subnet mask written in the dotted decimal notation, or in some cases you may see the binary forms. They're all the same value. Let's try host C4. The bomb. Let's do it over here. We'll do it quickly. I'll choose an address. So here's an IP address. I've selected that IP address just for the example. And let's say with this network C, we use a different subnet mask. That's possible. That different networks, we use a different number of bits that identify the network portion. Of course, a different subnet mask. In the first example, we use 10 bits. Let's say, just for this example, we use 20 bits. That is, the first 20 bits identify our network portion. The split would be, here's 8 bits, 16 here. First 20 bits identify the network C. The last 12 bits identify the device 4. So in different networks in our internet, we may use different subnet masks. That is, have this split between the network and host portion at different positions in the IP address. We'll talk a little bit about how do we choose the subnet mask. It's in fact assigned to us. But first we'll just explain the concepts. So if that's C4, then C3 must be, the first 20 bits must be identical, because C3 is on the same network. And the last 12 bits must be different from C4. These 12 bits are different from these 12 bits, so that's a different or a valid IP address. And the subnet mask, I won't write it, but we'd just write 20 ones followed by 12 zeros in the IP 32-bit value form. You can convert them to dotted decimal notation. This one, C4 becomes, I've done it before, 96.1.65.1 slash 20 if we use the slash notation for the subnet mask. The first 20 bits are the network portion. And C3 is 96.1. What do we have here? 64 plus 15 is 79.1 slash 20.
For the C4, is it 65 on the third number?
Yes. Good. (64 plus 1, 65. 64 plus 15, 79. So we're just introducing or explaining the rules that we must follow for the structure of the IP addresses. There's still some things missing about how do we know the split, or how do we choose where the split is, but we'll cover that shortly. All hosts on the same network have the same network portion of the address and a unique host portion. Another thing that we commonly use is instead of referring this as network A and this is network C, we give this an IP address to refer to a network. So the IP addresses that we've given so far refer to devices on a network. We can also have an address that refers to an entire network, referred to as a network address. And the way that we obtain the network address is, so the network address for network A, the network portion of the address is the same. The host portion of the address, the remaining bits, are all bit 0. So this is a special case address, a network address. It identifies our network A. Convert to dotted decimal and we get 16.192.0.0. So instead of me writing letter A here, I would write 16.192.0.0 subnet mask 10. So now I can talk about a network by referring to its network address rather than a letter. And computers can refer to that network using a network address. The network address and all the devices attached to that network have the same network portion and a different host portion. We will,
But for network C, the third digit should be different.
for network C, would apply the same approach, but you may see that the numbers here differ a little bit. You can try that in a moment. Let's stop now and I think have our course evaluation. And then, please. continue with IP addresses. If you finish the evaluation, find the network address for network C. What's the network address? No. What's the network address for this network? 96.1.0, no. 96.1.64.0/20. Why? The network address, the host portion is set to all zeros. So what we would have with the network address here, I won't write it. Okay, these 8 bits are the same, which become 96. These 8 bits will be the same, they're part of the network portion, they become 1, 96.1. Then we have 4 bits here, which must be the same, so it must be 0, 1, 0, 0, because they're part of the network portion. The remaining bits are all 0. So in fact, these 8 bits would be 0, 1, 0, 0, 0, 0, 0, 0. Convert that to decimal, and you get 64. And the last 8 bits would be all 0, hence we get 0. So network address, network 96.1.64.0, addresses of 2 hosts in that same network.
And the subnet is 1.1.1 for 20.
And the subnet mask is 20 ones followed by 12 zeros. And we can convert that to dotted decimal if we like. So be careful that depending on the subnet mask, in particular, if the split is somewhere, if it's not at one of these points here, then you need to be very careful as what is the network address. You need to look at the binary value to determine it. If the split was here after 8 bits, 16 or 24, you can actually look at the dotted decimal form and do a shortcut calculation to find the network address. But I advise you to look at it from this perspective. Network bits, all the same. Host bits are 0 for the network address. Network B would have a network address. We're not going to use an example there. So we would use these addresses in our routing tables, for example. If you recall back the routing tables, R1 may have a routing table. To reach network C, send to R2. In the routing table, we don't include the value C, we include the network address for network C. So that's where we can use the network address to refer to all the devices on that network. And instead of R2, we would include the IP address of R2. Routers have IP addresses as well. They are devices attached to a network. And in fact, each router would have an IP address for each interface it has. Router R1 has an interface on this network, so it would need an address like 16.192.0.3 would be a valid IP address. It would have a second IP address for this network. And R2 would have an IP address for this network and an IP address on this network. So your router would have one IP address for each network interface. So our routing tables do not include these letters and so on. They include network addresses and IP addresses of devices, of routers normally. A network address is a case of a special address. There are special types of addresses that we cannot use for our devices. So what do we know so far? Each device in our internet needs an IP address. A device is either a host or a router. In fact, more specifically, we can say each interface attached in our internet needs an IP address. Here's an interface that we have. It needs an IP address. The router has two interfaces. Each interface needs an IP address. Each interface has an IP address. Each network has a network address, and that should be unique. This network address, different from this, different from this, because they identify networks inside the wider internet. Each interface attached to one network must have unique IP addresses, and an IP address, and each interface attached to one network must have the same network portion of the address, but of course therefore a different host portion. So that's some of the rules that we need to apply when we give IP addresses to devices in the internet. There are some IP addresses that are reserved for special purposes. One example is the network address. My host cannot be given this address. It's a special case address. That is, my host cannot be given an address where the host bits are all 0. We're not allowed to do that. If we did, something would go wrong. Either the operating system would say you cannot set that address, or when you start to try and send datagrams in the internet, they will not be sent or not delivered to you. So you must be careful to set the addresses to the appropriate values, and you cannot set the device address to a network address. There are other such special case addresses, so let's go through them. A network address identifies a network or a subnet in the internet. All bits in the host portion are 0. We've gone through that. Sometimes we'd like to be able to send one datagram. This one wants to send one datagram and reach everyone on this network. This is called broadcast. I would like to be able to send one message and reach all recipients in some group. So broadcast a message. There are two types of broadcast available in the internet. One's called directed and one's called local broadcast. Let's go through directed broadcast. Directed broadcast is when some device on the internet wants to send an IP datagram to all devices attached to one particular subnet. For example, there are 3 devices on this subnet, R2, 4 and 3. If host 1 here wants to send a datagram to all of those devices, it would use directed broadcast. When you send to a specific device, you set the destination address to be the address of that device. If you want to send to multiple devices, all devices, you set the destination address to be the directed broadcast address. Let's determine what the directed broadcast address is, and then show an example of how it's used. Every network has a directed broadcast address, and it's the same for all devices in the network. It's easy to determine. A directed broadcast address, we take the same network portion, directed broadcast, this is for, we'll do it for network A. We take the same network portion and the host bits are set to 1, binary 1. This is the directed broadcast address for this network, 16.192.0.0. The way that I obtained it, we have our network portion, and which is the same for that particular network, and the host portion is set to all 1s. And we can convert to dotted decimal. It becomes 16.255 this address is used if someone else wants to reach all the hosts on this network. If host C4 wants to send a datagram with some data and an IP header, it wants to send this data to everyone on this network. Instead of sending one datagram to this host, one datagram to this host, instead of sending two separate datagrams, it can use this directed broadcast. It creates one datagram and sets the destination to be our directed broadcast address of that network, which is, what is it? 116.255. If you cannot read that, it's this address. 16.255.255.255. In fact, in the IP header, it's the 32-bit value.
And in datagram, we have to put /10 into the IP address.
No. In the datagram, it's only the IP address, not the subnet mask.
Subnet, no, only in that subnet.
In the datagram, in the header, if you go back to the description of that header, there were two 32-bit fields, the source IP address and destination IP address. We only include the IP address in the header, not the subnet mask. That leads to some complexity, and the way that we deal with the subnet masks is through the routing tables. The routing tables must be configured such that we can distinguish where this datagram should go to reach that subnet.
So the router will do this through the subnet mask.
The router would know about the subnet masks, yes.
Calculation, the exact.
Yeah, the router knows that. You'll see an example of a routing table with subnet masks. The idea now, this host creates one datagram, sends it to its router. The router would have a routing table, and if everything's correct, it would send on to router R1. R1 would see this datagram, see that the destination is the directed broadcast address for its network. And when it sees that, it would know, okay, I need to now make copies of this datagram. Send one copy to this host, one copy to this host. If I had 100 other hosts there, it would send a copy to each of them. So the idea here is that we send one copy of the datagram across the internet until it reaches the last router, and then that sends multiple copies to the destination hosts. That's much more efficient than using the normal approach of sending one copy all across the internet to this host, sending another copy all across the internet to this host, and to all the other potential destination hosts. So that's where a directed broadcast address can be used. The broadcast is directed to a particular network. The other type of address is a local broadcast. And this is broadcast in your network, in the network that you're attached to. If this host now wants to send a datagram to everyone on its own network, not on some other network, but on its own local network, then it can set the destination to be a local broadcast address. And there's just one local broadcast address. It's where all 32 bits are 1. So 32 ones. A special case, or in dotted decimal, 255.255.255.255. Set the destination to that. You cannot read that, but that's the local broadcast address. What that means is that the network will deliver a copy of that to everyone in the local network. This will receive a copy, the router will receive a copy, and anyone else attached will receive a copy of that. In this case, this is useful if, for example, this device doesn't doesn't know its IP address yet. You turn on your computer. You don't have an IP address. You just turn on the computer first time ever, and you want to find an IP address. You want someone to give you an IP address. This could be used. I turn on my computer. I send a datagram destined to this special local broadcast address. I don't know anything about this network. I don't know it's 96.1.64.0. So I send to this address, and hopefully there'll be a special device on this network that may respond. And that concept is, we're not going to cover in this course, but you may have heard of DHCP. You contact a DHCP server and get an IP address. This address can be used to do that. If we don't have an address yet, sometimes we'd like to automatically discover an IP address, get one allocated from someone else, and we can make use of the the local broadcast address. If I turn on my computer and I don't have an IP address, and I send an IP datagram destined to 255.255.255.255, what's the source address in that datagram? I don't have an IP address. I send a datagram. Remember, the header has a source address and a destination. This is the destination. What's the value of the source address? All zeros. There's another special case, the startup source address. It's all zeros, 0.0.0.0, 4 zeros. Okay, so that's another special case address. And it's used in that same process of, you don't have an IP address yet, you can make use of these two special addresses, the startup source address and the local broadcast address, to try and ask someone if they will give you an IP address. And then you can configure your own IP address after that. Yeah, 4 zeros. Yeah, 32 zeros in binary, which becomes 4 zeros in dotted decimal notation. So there's an address that identifies each network. For each network, there's a directed broadcast address, which is used if you want to send a message to everyone on a particular network. In practice, that's not used in the internet, or it's not allowed in the internet much. That is, if it was allowed, then I could create a datagram and send it to everyone on Facebook's network. If I knew their IP address, or I send to everyone at Microsoft, and all 10,000 computers on their network would receive my message, and we could, of course, perform security attacks and spam them with messages, really. So, in theory, we have a directed broadcast address. In practice, it may be limited as to how far you can send it across the network, across the internet. That is, this router may block it from sending any further. But in theory, we can do it. Local broadcast, send to everyone on your local network. Startup source address is only used when you don't have an IP address for very special cases and you want to discover an IP address, the all zeros value. One last special case, the loopback address. You want to send to yourself. Imagine you have a computer, you have a cable that comes out and it comes back into your computer. It loops back into your computer. You don't necessarily have a cable, but your operating system will handle this loopback address. If you send to this destination loopback address, you will receive a copy of that datagram. You will receive it. Send to yourself, basically. And the structure of the loopback address, the first 8 bits follow this pattern. 0 followed by 7 ones. The rest can be anything in theory. Have we got some space? First 8 bits of this sequence, the last 24 bits can be any value, and it's a loopback address. The most common one you'll see I can't remember how many, I've lost count. That's a very common loopback address you'll see. In theory, anything that starts with 0 followed by 7 ones, or in decimal, 127. But in practice, you'll commonly see 127001. Others you may see as well. If you send an IP datagram where that is the destination address, you will receive that datagram. No one else will receive it. Useful for testing things. You want to access some service on your computer, send to that local loopback address, and you'll receive a copy of that datagram. Of course, on your computer you can see some of these addresses. This is my Ethernet interface. Before the lecture I plugged in an Ethernet cable and obtained an IP address. In fact, the way that I got this IP address, 10.10.103.54, was using DHCP. In fact, although it's not shown here, my computer sent a special message to this local broadcast address with the source to be the special startup address, and some DHCP server in SIT responded and gave me this IP address 10.10.103.54. And it gave me the subnet mask 255.255.248.0. And from those two pieces of information, the mask and the IP address, I can determine the broadcast, the directed broadcast address, 10.10.103.255. So there's 3 addresses that my Ethernet wired interface had obtained.
So we have 8.16 but lost to the last input of that group is 00 and 111. So the mark is 16 broken.
Yeah, 248 is what? Minus 17 and minus 7.
24, first 24 is the network, and the last is the phone.
Someone will go and work that out for their homework. What is this address in binary? 255.255.248.0. And convert it to the slash notation. So remember, this is the dotted decimal notation. You can convert it to the real binary notation and work out how many ones and how many zeros that we have. Multicast. So broadcast is send to everyone in a particular network. Unicast is the normal approach, send to one device in a particular network. So normally we use unicast. 4 sends to 1, unicast. 4 sends to everyone on this network, broadcast. Multicast, 4 sends to a selection of the nodes in some network, is multicast. You send to a select group of nodes. For that to work, you need multicast addresses, but you need something else. You need somehow to know which nodes are in a particular group. You can cover multicast in Internet Technologies if you choose it as an option next semester, if it's possible. Addresses of my interface for my wired LAN. If my wireless LAN could connect, I'd get an IP address, a different IP address for the wireless LAN, but it cannot connect here. I don't have a strong enough signal, or I couldn't before. And my loopback address. Your computer normally treats this special case loopback interface just as another interface. This 127001 address, and it has a mask as well. The first 8 bits represent the network, this 127 network. So if I open up my web browser and type in the destination address to be 127001, then my computer would send an IP datagram to itself. It doesn't go out onto a network, it remains within the operating system and is transmitted and received by itself. And if I had a web server on my computer, I would see the web page of that web server. So used for testing. Okay, that's the main structure of the addresses. We've missed, or there's a couple of other things we need to talk about. How do we get a subnet mask? In particular, how do we get a network address? Why did I have a subnet mask which says the first 10 bits here and over here the first 20 bits? Yeah, so the difference, or one difference between these two subnet masks is what's the maximum number of interfaces or devices that can be attached to that individual subnet or network. Let's see. With our subnet mask, in this example, the first 10 bits are the network portion. Therefore, the last 22 bits are the host portion. Every host attached to that network must have a unique host portion. So host A1, the first 10 bits are the same with host A2. The last 22 bits must be different. Host A3 must have a different last 22 bits. And A4, A5, if you want to attach more hosts, with 22 bits, the number of possible values we have is 2 to the power of 22. So we can vary those 22 bits and we get 2 to the power of 22 possible values. 2 of those values we cannot assign to hosts. Which 2 values? Of those 2 to the power of 122 values, which ones cannot be assigned to hosts?
1 or 1?
1 or 1? No, I think we got it. The first one or the last one, that is all zeros and all ones. If I had to write these down on the board, then the first one I'd write is 22 zeros. I cannot give this address to a device in my network because that is reserved for the network address, which is in fact this one. When we have 22 zeros, that gives us a special case address, the network address. So I cannot give that to a device in my network. And another one that we cannot give to a device in the network is the directed broadcast address, 22 ones. So the number of devices or hosts that I can attach to my network is 2 to the power of 22 minus those 2 special cases that I cannot use. Cannot use all 0, cannot use all 1. All other values I could assign to different hosts. It's about 4 million. Correct? Yeah. So with this subnet mask, the maximum number of hosts that can attach to this subnet is about 4 million. 2 to the power of 22 minus 2. Note that that includes the router. The router needs one of those IP addresses. When I say the number of hosts over there, I mean really the number of devices that can attach. Include the router. That is the number of IP addresses that we can assign to different devices. In this case, we had a split of 20 bits followed by 12 bits for the host portion. Same principle, we have 12 bits to assign to different devices, giving us 2 to the power of 12 different options, but we cannot use all zeros and we cannot use all ones. What is it? In this subnet C, where we have the subnet mask of a /20, we have 12 bits for the host portion, giving us 2 to the power of 12 possible values, minus the 2 special cases we cannot use. In this subnet, we could allocate 4,094 IP addresses to devices. 1, 2, 3, and another 4,091 addresses. So the maximum number of devices that we can attach to a particular network depends upon the subnet mask. Here we can attach 4,000. In subnet A, we could attach 4 million. What about SIT? Okay, questions?
I was thinking about, let's see if there are two computers in different networks, but they happen to have the same IP address, but a different subnet mask. Is that large valid address?
We'll talk.
The network portion is different.
The subnet masks are assigned according to some scheme such that all addresses should be unique within the internet. So you cannot choose your own subnet mask. Someone gives it to you, and the person that gives it to you makes sure that what they give you is not going to cause a clash with someone else in the internet. So that we'll assume that that works. I'll say a little bit more about that in a moment. So the more bits in our host portion, the more devices we can attach to our network. How many bits do we need for SIT? So a typical exam or quiz question, SIT has 500 computers. You get a wrong answer. SIT has 500 computers. We want to attach 500 computers to our one network. How many bits do we need in the host portion? 9 bits.
9 bits for host.
9 bits in the host portion. 2 to the power of 9 is 512, minus 2 is 510. If I have 500 computers, with a 9-bit host portion, I could allocate a maximum of 510 IP addresses. So we can start to design or a particular subnet mask depending upon the size of the network that we want to allocate IP addresses. If I'm an internet service provider, everyone who who has an ADSL connection, I give an IP address. TOT, when you connect to their network, gives you an IP address. It has 100,000 customers. Therefore, it needs a host portion large enough to give IP addresses to those 100,000 users and to be unique. So the subnet mask, or the number of bits in the host portion, which is determined by the subnet mask, is related to how large of a network that we want to create, how many devices we want to attach. So we'd like to have a large enough number of host bits to support the number of devices in our network, but the more bits that we allocate to the host portion, the less bits we have for the network portion. And the network portion identifies networks in the internet. The less bits we have for the network portion, the less networks we can have in the internet. So there's a trade-off there. How many networks in the internet? Well, on the order of hundreds of thousands. So each organisation in the world may have multiple networks. There may be hundreds of thousands of different networks needed in the internet. So in fact, today, the way that IP addresses are assigned, we've seen the example. You can calculate this. We'll come back to it at the end. Classful IP addressing we're not covering. You can read through if you wish. How do you get an IP address? IP addresses, we have 32 bits. We have 2 to the power of 32 possible values, but in fact structured by network and host. They are managed by some central organisation, the Internet Assigned Numbers Authority. What it does is it takes the space of IP addresses, allocates some to one region of the world, one to North America, one to Europe, and one set of IP addresses to Asia Pacific. So in the Asia Pacific region, there's APNIC, which is an organisation that manages the assignment of IP addresses in the Asia Pacific region. And in fact, that delegates the management to national authorities. In Thailand, THNIC. This organisation is the organisation you may go to if your company wants a range of IP addresses. More specifically, you want to attach a network to the internet, you need a network address, such as 96.164.0/20. This is assigned to you by one of these national authorities. They manage such that if they assign you 96.164.0/20, it should be unique within the internet, or at least unique within Thailand. And since the ones managed in Thailand must be unique within Asia Pacific, and the ones in Asia Pacific are unique within the globe, then your network should be unique within the world. So in fact, organizations who want to attach a network to the internet are assigned a network address and a subnet mask. The subnet mask would depend upon what their requirements are for the number of devices. SIT may need a subnet mask /20 or /22. A larger organisation may need a subnet mask /16 or /12 because they have a larger number of hosts that they want to attach. The network address would be assigned so that it's unique.
The slash is the number of network of hosts.
The slash is the number of bits in the network portion.
Okay. It's the big, the less host, with the small.
Yeah.
Big,
the larger this, the less hosts.
yeah.
The smaller it is, the more hosts. The bigger the network.
So the big organization needs
Smaller value. So a big organisation may be /10, and a small organisation may be /20, as an example. So this is assigned by these national authorities. Then your company has this. Then it's up to you, as the person who manages the network for that company, to give each device an IP address within this range. You can give this one .1, this one 79.1, and so long as all the devices in your network meet the rules, which are defined by this network address and this subnet mask, then you can assign them as you wish. You can manually do it. You can go to every computer in your network and type in the IP address, or on larger networks you can use things like Dhcp to automatically assign the computer's IP addresses. So that's something about where do these subnet masks come from. In fact, allocated via some global, regional and national authorities, so they maintain unique addresses.
the network IP address should be received for NIC or something.
Yes.
Provide. They cannot produce for their own for network IP address, but they can produce for the host address.
Yes, the network address and the subnet mask are assigned to your organisation.
Yeah.
The individual IP addresses are then up to you to assign to the devices.
By subnet mask.
Yeah, so long as it meets the rules that the network portion is the same. And these two addresses meet the rules that they have the same network portion as this.
And when we use the subnet mask, our address will not duplicate for another organization address.
Yes, it would not be a duplicate of someone else because the way that the subnet masks are allocated and the network addresses are such that they will not be duplicates anywhere else. And there's a special way to do that, having some hierarchy. That's a little bit more complex.
So it can duplicate, but it's not seen by other networks.
No, it's unique. But there's some there's a hierarchical manner in which the network addresses are assigned. And the way that the networks are structured in the internet, such that routing, that's what we care about, getting the packet to the right destination, routing will always deliver to the correct destination. I don't want to cover that, it takes a whole lecture or two. We cover that in Internet Technologies and Applications next semester, if you choose it as an elective. Coming back, this example, from the IP address of a device and the subnet mask, so typical questions you may see, find the network address What is it? Calculate the network address for this computer. That's 61 in binary. Our address 104.209.61.169/18 tells us the first 18 bits are the network portion. Whatever 104 is in binary, it's going to be 8 bits. Whatever 209 is in binary, another 8 bits, that's 16 bits. And 61 in binary is 00111101. So /18 says the first 18 bits of this address are the network portion. You can find out what this value is, but I know it's going to be 8 bits. This is going to be 8 bits. So 16, and the split's going to be here. 8 plus 8 is 16, plus another 2 is 18 bits. Followed by these 6 bits and the remaining 8 bits of 169. So 14 bits in the host portion, network portion, and the host portion. So the subnet mask tells us where the split is. The network address, we set the host portion to all zeros. So it's going to be these 8 bits, these 8 bits, 2 zeros, that is these 2 bits, followed by all zeros. Gives us the network address. And if we convert back to dotted decimal notation, we haven't changed these 8 bits, so we're going to get 104. We haven't changed these 8 bits, we're going to get 209. These 8 bits gives us 0 and 0. That's our network address, 104.209.00. Directed broadcast address, same approach, except instead of all zeros here, we have all ones. So we're going to have 104.209, and the third set of 8 bits will be 00 followed by 6 ones, which is what? $65? 63. 255. The directed broadcast address is 104.209.63.255. So you can of course find these values in binary. There's nothing wrong with that. So you've got 8 bits, 8 bits, 8 bits, 8 bits. Use the subnet mask to tell us where the split is. Network address, set the host bits to 0, convert back to dotted decimal. Directed broadcast, set the host bits to 1, convert back to dotted decimal. The way I did it was just saving and converting here. How many IP devices can be attached to my network? 14 bits in the host portion, gives us 2 to the 14 possible values minus these 2. We cannot use these for IP addresses for devices, which is whatever it is. So you can work out, given that information, what is the network address, what is the directed broadcast address, and how large the network can be in practice. If I wanted to support more devices, I would need a different network mask.